So welcome back. Happy Wednesday. We'll take our look at the calendar here first. So today we are doing polynomial optimization problems. It's a big topic for us. It is all the way in chapter 4. You can see that after today, we're not back in chapter 4 again for like a week, and then not again for a couple more weeks after that. So this is like the hardest material for a while, and then we'll kind of go back and fill in some of the things that we sort of skipped over. Polynomial optimization. So we started this just a little bit the other day, and I'll remind you of what we did in just a couple of minutes. Before I do, I want to point to the coming class on Friday. I will hand you quiz number 1 on Friday. You will put it away because Friday is not a quiz day. It's just a hand out the quiz day. So quiz number 1 is a take home. You will do it over the weekend and hand it to me at 10:40 Monday morning. And on Friday, when I hand it to you, I will remind you of the following rules, but I'll just put them out there just so you have a sense of what to expect. The quiz is an individual effort as opposed to the projects and the homework and studying and group work and all the other stuff we do together. When you are taking the quiz, you're allowed to use a 1-page reference sheet of your own creation. You can put anything you want on there, theorems, definitions, formulas, practice problems with solution steps written all the way out, anything you want, but you got to make it before the quiz starts. And it should be yours, not a photocopy of something from the book or something from my packet. You can't use any other reference materials. No open book, no open packet, no internet, none of the other stuff. Just a 1-page sheet, front and back, anything you want. You can use a scientific calculator only, but you can't use a graphing calculator. You can't use your cell phone. You can't use anything else with batteries. Scientific calculator only. There are lots of sources for problems as you study. You got the entire packet with the activities and the even more practice. You got all the homework problems. You got all kinds of homework problems I never assigned, but if you want more practice, certainly you can find problems in the textbook that I didn't assign. And in terms of the material that's on the quiz, it's lessons 1 through 7. Today is number 7, so it goes through today is the new material for the quiz. I have a, on the top of the quiz, it says recommended time limit is 36 minutes. You can ignore it. You can take as little or as much time as you want over the weekend. But don't spend 3 hours on this. That is not a good use of your time, honestly. The quiz is supposed to be a low value assessment, an opportunity here before we get to our test in a couple of weeks, an opportunity to see if you are roughly where I think you should be at this point in the semester. The quiz is worth 0.8%, a little less than 1% of your grade at the end of the semester. It's not worth a lot. It's just supposed to be a quick check-in. So 36 minutes, I think, is about how long I want it to take. If you want to take an hour on it, okay, but really don't take 3 hours. Like spend the other 2 hours on the projects. They're worth a lot more than this quiz, okay? All right, I think that's it. Any questions on the quiz? Again, I'll hand it out Friday. Okay, and then one other thing before we jump in. Somebody pointed out, this is page 20 of the first project, the arbitration one. If it's handy, you can grab it. Otherwise, just make a note. But somebody pointed out that I had crossed off in this project all of the problems I didn't want you to do, that I forgot to cross off number 9. So it's crossed off here just because I did it this morning. But on this page, which is page 20 on the top left of the page, you can feel free to cross off number 9 if you want. On the first page, it tells you exactly which problems I need you to do, but someone pointed out that the others were crossed off and was wondering why this one was not. That was just an oversight. Okay. All right, so let's jump in here on the bottom of page 48. So here's our first question. Without using a graph, find the absolute extrema of f of x equals 2x cubed minus 3x squared minus 72x plus 5 on the interval -6 to 8. Okay, so remember, extreme means high and or low. So we're looking for the high and or low points of that function. And we want the absolute ones as contrasted with the local ones. We want the absolute highest point anywhere on that interval and the absolute lowest point anywhere on that interval. Have we played around with GeoGebra in this class before? Have I showed this? Yeah? Okay, so let me just make the thing bigger for you guys. All right, can somebody read to me that function real quick? Thank you. Okay, so I'm just typing it in as usual. We'll caret, the up arrow is the power. So there's the function. It's really hard for me to see it here, so that button right there allows me to just take an axis and drag it. And so very quickly I can get a good view of this function. And the interval was from where to where? -6 over to 8. Let's drag just a little bit this way. Okay. All right. So between -6 and 8. So I can even put points there. If I say -6 comma f of -6, it will put a dot right there, and then 8 comma f of 8. Okay, so with the benefit of this wonderful technology, where is the highest point anywhere between those two ends? Is B, right? B is the highest point. It's higher than any other place. Is A the lowest point? No. The lowest point is down here someplace, right? There are lots of points down here that are lower than A. So ultimately, we're trying to find this bottom point. If it's a nice number and we can read it off the graph, it sure looks like it's right around 4. Yeah? Okay, so it looks like we want to come up to this conclusion that 4 is the absolute lowest point anywhere between these two ends, and B, 8, is the absolute highest point anywhere between these two ends. The question is, can we get those exact same answers without knowing what the graph looks like, without having any of this insight that the software has given us? So that's the goal. Okay, so let's see if we can get to those answers using calculus and algebra. So I will say this is a very standard calculus problem. Find the absolute extrema of a function on a closed interval. Standard Calc 1 problem, and it has a standard Calc 1 solution. We're going to do that right here. We're going to make a table. And there's two kinds of things we're going to put in this table. One kind of thing are the endpoints. And so let's go ahead and put -6 and 8 right there. Endpoints. Because for sure, the endpoints are candidates for being the highest or lowest points, right? And in fact, on this particular one, we know ahead of time the right-hand endpoint is going to turn out to be the highest point anywhere. So the endpoints are always candidates. And then the other points that are candidates are places where the graph is flat. And so out here, it looks like x equals 4 was our answer, but for sure, I know that the tangent line is horizontal at that low point, right? The tangent line is also going to be horizontal at this high point. Turns out I don't care about that high point, but I don't know that ahead of time. And so then the other place that we look for are points where the tangent line is horizontal. We gave those points a name the other day. We called them critical points or critical numbers. And so let's find the critical points. And finding the critical points is always done exactly the same way, regardless of the function. You take the derivative of the function. So let's do that using our newfound rules. So 2x cubed, the 3 comes down, multiplies by the 2, gives me a 6. X to what power? Squared. Good. Same idea for the -3x squared, minus 6x to the first. You don't need to write the first. And then -72x, that's a -72. And what about that +5? 0, we're not even going to write it. So we take our derivative. And remember, the derivative is the slope of the tangent line, and I'm looking for horizontal tangent lines. So what slope, what number slope am I looking for? 0, right? Every horizontal line has a slope of 0. So we take the derivative and we set it equal to 0. And in your past math classes, you spent a lot of time solving quadratic equations equal to 0. And now finally, like an opportunity to actually it comes up in like a reasonable context here in calculus. So what can I factor out of all these? 6. Yeah, you could do the quadratic formula now, but it turns out this one factors. So let's practice factoring. So 6 coming outside of everybody. Fill in the blank parentheses for me. So I get x squared minus x minus 12. And then the thing in the big parentheses is going to factor into 2 smaller sets of parentheses. Some of you are very quick with this. Some of you take a little bit more time. It's okay. Take your time doing this in the homework, but for right now, we'll just put the answer up. I think it's an x minus 4 and an x plus 3. And then we said each of the pieces equal to 0. So either x minus 4 is 0 or x plus 3 is 0. And if you're a completionist, there's actually one other thing equal to 0 that I didn't write, but I could have. 6 equals 0, right? I mean, you shouldn't ignore it. It's there. Every one of these factors equals 0 is a candidate. And so then solving these equations is easy. X equals 4, x equals negative 3, 6 equals 0. It does not. So our critical points are 4 and negative 3. Yeah? And so we take our critical points and we put them right over here in our table. 4, negative 3, critical points. Happens, there's 2 of them. There could have been 3, there could be 1, there could be none. We don't know. You're just solving the equation equal to 0, and whatever you get, you get. Okay, and then the last piece of this puzzle is to figure out what we plug all these x's into. There's 2 functions that are sitting up on this page right now. What are the names of the 2 functions? F and f prime, right? Those are the 2 functions. Only one of them is the one that's relevant to us. Plugging these things into f prime would tell you the slopes of various tangent lines. What's the slope of the tangent line at 4? It's 0. That's how we found it. What's the slope at negative 3? It's 0. That's how we found that. And that doesn't help me know whether one of these is the highest or lowest point or none of the above. Knowing the slope at negative 6 and 8 would only tell me whether the function was going up or going down, but still wouldn't tell me like how high or how low it is. And since that's what we're interested in, how high or how low, we got to plug into f. So like I said, standard calculus procedure. Hopefully it makes sense that we put f there, not f prime. Okay, so just to save time, I'm going to go back to my software and ask the GeoGebra to tell me the answers. So we actually got 2 of these already. Write these down. So at negative 6, it was negative 103. And at 8, it was 261. You could do this on the calculator later. We're just saving time. And then the critical point, f of 4, okay, that turns out to be negative 203. That's for 4. At 4, it's negative 203. And then f of, what was the other one? Negative 3. Yeah, and that's 140. 140. Okay, so somebody tell me the numbers in order. $140? Okay. All right, and so without having the picture in front of us, we're supposed to look at these numbers and know which one is the highest. Because you're looking for the biggest y value. Where is it? 261 at x equals 8? Yeah, of course. And that's what we knew ahead of time because we had the technology, but that right there is your absolute maximum. 8, 261, the far right-hand point. And the absolute minimum is the lowest point anywhere, which is the smallest y value we found, which was negative 203. Absolute min. And that's it. Yeah, Aaron. So we're finding the zeros for original function. Yes. Okay. So just to summarize, absolute extrema on closed interval. This problem you're going to see again and again. This is always the process. Take your endpoints and your critical points and plug them into the original function. Pick your highest and lowest values and call it done. Questions? Okay, and just to take like a 30-second overview or step backwards from this problem, this is like the first of a bunch of optimization questions that we're going to tackle this semester. To optimize something outside of a math class means roughly make it as good as possible, whatever good means in the context. For us, it's going to be more specific. It's going to be take a function and make it as big and or as small as possible. Biggest y value and or smallest y value is exactly what we did here without any context, and it's what you're doing on the arbitrating disputes project. You're trying to maximize the joint happiness function as big as possible. And for the truck problem, you're trying to minimize the cost function. Okay, and on the next page, let's tackle a word problem. A math book is to contain 36 square inches of printed matter per page with margins of 1 inch along the sides and 1.5 inches along the top and the bottom. All right, so before we jump in, give me some dimensions that would give me 36 square inches for my rectangle. Could be a 6 by 6. Could be a 12 by 3. Could be a really thin 2-inch wide, 18-inch tall book. Could be. Any other possibilities? Could be a 9 by 4. Could be like a 36 by 1. Is that it? I've got 5 choices, right? Those are all the things that multiply to 36. Daniel? Everything in between, get out of here. 7 by what? 7 by something. 5 1/7. I'll write it this way, but yeah. 5 1/7, right? How many possibilities are there? Infinitely many. Got infinitely many choices for rectangles that have an area of 36. We are going to pick the one that optimizes something. I don't know yet, but there's a lot of choices. We have to whittle it down to the best one, whatever best means. So it says you got margins of 1 inch along the sides and 1.5 inches along the top and the bottom. Okay, fair enough. Find the dimensions of the page that will require the minimum amount of paper and find the minimum amount of paper. Okay, so that word right there clues me into this being an optimization question. I am going to create a function and then I'm going to make that function as small as possible. And that will be my answer to this problem. So let's draw a rectangle. And then outside of that, draw another rectangle. And so inside of here is the printed stuff. And then it's blanks around the edges, that's the margins. So we'll fill in the blanks. It says 1 inch along the sides. So I think that means that it's 1 from here to here and also 1 there to there. And 1.5 inches on the top and the bottom. And what we want to do is figure out what the length and the width are supposed to be to make the total amount of paper as small as possible. Minimum amount of paper, that makes sense, probably has the minimum cost. Okay, so if there weren't margins involved, how many square inches of paper would we use for our 6 by 6? 36 square inches, right? And if we had a 12 by 3, 36 square inches. If there's no margins, these are all tied for first place, tied for last place. It makes no difference. You're using 36 inches of paper, however you slice it in terms of length and the width. But having these margins fixed throws everything off and makes it so that actually there is going to be a winner, a smallest piece of paper altogether. So let's go ahead and label some stuff. So let's call length here, and then width can be going across, but without the margins, okay? So we'll call L and W length and width, not including the margin part. All right, and it's written here in the hint, you know, let L be the length and W be the width. If that weren't written there, you would need to write that in words. Let L equal the length. And in fact, I was lazy here. I should have included a unit word. Length in inches is what I should have said there. All right, so let's come up with our formula. So here's a fact. We know that there's 36 inches of printed matter per page, which means L times W is definitely 36 for every one of our possibilities, right? All right, don't know how we're going to use that just yet, but it's there. And now we're going to write a formula for area. And when I say area, I mean the entire page, the total page, including the printed stuff and the margins. What's a good expression for the entire length? Yeah, L plus 3, right? Because it's the blue L plus the purple 1.5, two of them. So it's L plus 3 altogether. And then a good name for the width of the whole thing? W plus 2. There we go. Okay. So this is the function that I'm trying to minimize. I'm looking for the minimum amount of paper. That's the number of square inches of paper. And I want to make that as small as possible. The problem is there are two input variables for that function. It's got an L and it's got a W. And everything we're doing this semester is going to involve one input variable at the end of the day. And so I need to substitute. I need to replace one of these L's or W's with the other. Yeah. So let's solve this guy for W. It doesn't matter which one we solve for, but we'll solve for W by dividing both sides by L. And then we can use that to substitute into our other equation. So this becomes L plus 3 times the new 36 over L plus 2. Okay, let's distribute this. Not ready to do any calculus just yet, but foiling first times first gives me 36, right? Because the L's cancel, that's convenient. Plus outers, 2L, plus inners. Yeah, so 3 times 36 is 108. 108 divided by L, that sounds good. And then plus the last 6. It's all plus. All plus. Okay, that's good. We'll just combine like terms here and get our simplified answer. So area equals, so the 36 plus the 6 joins to make 42 plus 2L plus 108 over L. All right, so there is our total page area function. It's as clean as it's going to get. It now has how many input variables? Just one. And so now we can do our calculus on it. We are looking to make that function as small as possible. We know that if you are at a minimum point, like a turning point, what can you say about that tangent line down there? It's horizontal, and so the slope is 0. And so we're doing something quite similar to what we did on the previous problem, is we are taking the derivative and making it equal 0. So here we go. A prime equals, what's the derivative of the 42? 0. So we're not going to write that. Derivative of the plus 2L, just plain old 2. 108 over L. Yeah, this is one of the shortcuts I'm encouraging you to remember. A constant over x, we talked about that last time, is negative the constant over x squared. So that becomes negative 108 over L squared. Okay, and this is our derivative, and I want a horizontal tangent line, so I want that derivative to be 0. So I go out of my way to set the derivative equal to 0. And now I got some algebra to do. And in some math class in your past, you solved equations that look like this, and now you actually get to use them in the middle of a bigger problem. So how about we add the 108 over L squared to both sides? So 2 equals 108 over L squared. And then we'll get rid of the fraction by multiplying both sides by that denominator times L squared on both sides. So 2L squared equals 108. And then we'll divide both sides by 2. L squared is 54. and then the square root of both sides, square root of 54. Technically, I'm missing something. What is it? Yeah. Right. When you take the square root, you put in plus or minus. But then we say, hey, L is a length, and it can't possibly be negative square root of 54. So we'll reject that one. And then square root of 54, I guess we can reduce that, right? 9 goes in 6 times. I think it's this, 3 root 6. I think that's okay. And just to be, sort of like really concrete, as a decimal, 7, 5, 7, 4, something, 7, 4, 5. What is it? 7, 3, 5. Okay. All right. So here's what I know. If I were to look at a graph of the entire page's area function, that function changes based on what length you choose. All the lengths that we pick are going to have, still going to have 36 square inches of printed stuff. But of all the lengths that we could pick, that one right there on the total area graph has a horizontal tangent line. Does that mean that's the minimum point on the graph? Couldn't a horizontal tangent line be the maximum point on the graph? Saying that the tangent line is horizontal tells you, hey, you might be at one of the extremes, but it doesn't give you any clue as to which one you're at. And so if this is our job to find like the smallest piece of paper, we better not stop here because that might be the absolute worst, biggest piece of paper possible. So instead we do a tiny bit more work. So here's something brand new for us this semester. It's our very first sign test. And what we're going to do is we're going to put our answer, our number, our critical point right there on the number line. So we're going to put square root of 54. But again, if you want to be concrete, it's right around 7.35. That's the number line. And we're also going to put on this number line any implied domain for this problem. What's the smallest L you could possibly have? Like that makes sense? 0, right? I mean, like, and you can't say, all right, so 0 doesn't make sense. But you can't tell me that 0.01 is the smallest because I could name something smaller than that that still makes sense. So we'll put 0, even though like 0 doesn't make sense, but we can't put any other number there. So we'll put 0. And how about the biggest L? Like, could L be 100 inches? And we'd still have, could it be bigger than 36 or no? No? What if it were 100 by something? What number can I put there to make it equal 36 at the end of the day? Doesn't that multiply to 36? Yeah. So there's no biggest, there's no end on the far right. Okay, so we've got our number line here. And now we are going to do a sign test. And the thing we're going to do is take the intervals that we've cut this number line into and plug them into the derivative function. The previous problem, we plugged into the original function. Here, we're plugging into the derivative. So I'm going to call this guy A prime. That's the number line. That's the label on the number line. So let's pick a number between 0 and 7.35. 6. We're going to take that 6, we're going to plug it into the derivative function. So I'm plugging a 6 right in here. 2 minus 108 over 6 squared. I actually don't care about the number, so if you're reaching for your calculator, you're doing more work than I want you to be doing. I just want to know if it's a positive answer or a negative answer, nothing more. So I'm plugging 6 in here. 108 over 36, I don't know, it's like 3-ish. 2 minus 3 is negative. And in fact, we would get a negative, so I'm going to put a little negative sign up here. We would get a negative not just for plugging 6 in, but for plugging in 5 and 4 and 3 and 2 and 1 and pi and anything between 0 and the 7.35. For me, I would have plugged in 1, and I'd say, hey, 2 minus 108 over 1. Is that positive or negative? Negative. In fact, picking 6 is, well, 6 is kind of close to the 7.35, and the closer you are to the critical point, the closer to 0 your answer is going to be, and I don't want anything anywhere near 0, because all I care about is positive or negative. So I typically pick numbers that are far, from the critical points. So negative, any place between 0 and root 54, and then something bigger than this number. 8 is fine, 100 is better. 100 is my go-to, something wildly outside of this range. And so I'm going to pick 100 and plug it in for here. 100 for L. 100 squared, that's 10,000 on the bottom. 2 minus 108 over 10,000. Is it positive or is it negative? Positive, because 108 over 10,000 is pretty close to 0. And so 2 minus pretty close to 0 is positive. And any number we had picked bigger than root 54 would have given us something positive. And so here's what's going on. Between 0 and root 54, the tangent lines are downhill, negatively sloped. And then, when you get past root 54, they are uphill, positively sloped. So you imagine a graph that goes downhill, downhill, downhill until we get to the 7.35 length, and then uphill, 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 forever, increasing forever. What can you now say about that 7.35? It is a minimum. Hey, that's good. That's what we were after, right? So that's how we justify, and we write the following sentence to make sure that we're really clear in explaining that number line. So here it goes. A required justification that's typical at the end of a max or min problem. Since A or A prime, what did we just plug into up there? A prime. Since A prime is the derivative of the area, goes from, what was it to the left? Negative. Goes from negative to positive at, and then you write down the input value. It was L equals root 54. And now we're about to describe whether we have a local min or max. Is this a local min or max on A or A prime? It is A. And in this case, we had a local min at, and then we write exactly the same input value that we did before. L equals root 54. Okay, so there's our sentence. It's always an A prime in the beginning, and it's always positive, negative stuff. Maybe the order is different. And then it's always A having a max or a min, okay? Think of it like the Mad Libs used to fill out in junior high school, just like fewer toilet references, right? So this is it's almost as much fun. I think this is an untapped market, like calculus Mad Libs. You could just like. All right, last piece of this puzzle was to actually find the area, I think, right? It says find the minimum amount of paper. So we'll do that real quick. The minimum amount of paper, meaning the actual area. So if I put my final answer in here, so the area when I have a, root 54, just plugging it in for those two L's. 42 plus 2 root 54 plus 108 over root 54. And if somebody could get me a decimal, that would be good. So while we're waiting on a decimal, let's move on to number 10 here. It's one of our first named theorems of the semester. It's called the first derivative test. It says suppose that f is continuous and has a critical number at x sub 0. So that's going to be our special x value. And then we're going to fill in some more blanks here. Anybody have a number for us on this? Again? 71.39 square inches is the minimum amount of paper that we can use. Okay. All right, so let's take a look at the first derivative test down here. So if f prime of x is negative immediately to the left of a special point, and then positive immediately to the right, so I'm imagining negative, decreasing, positive, increasing. What are you looking at down there? That is a relative min. So fill that in the first blank. Relative minimum. And then the other case, if f prime is positive to the left and negative to the right, going up and then going down, we have a relative max. And if f prime has the same sign on both sides, so for example, it's positive and then it's flat for a second because that's how we found the critical point in the beginning, and then it's positive again. So it goes uphill and then briefly horizontal and then uphill again. Is that a max or min or neither? It is neither. And likewise, if it was decreasing and then decreasing again, it would be neither. So that's what it says there. F has neither a relative max or min. You could visualize x cubed. It's like the standard example, right? It goes up, goes through the origin, briefly horizontal, and then continues going up. Okay, so 2 fundamental processes in Calc 1. Here are the steps to find relative extrema. Find the critical points and do a sign test. That's what we did up above. Local max, local min. To find absolute extrema on a closed interval, evaluate the function at the critical points and the endpoints, and then pick highest and lowest function values. Okay? All right. Activity starts on the next page. Let's see how far we can get.